All right. Good morning, everybody. Hold on. Last minute kinailangan ko mag-restart ng iPad kasi ayaw magbukas ng Notability ko. Pero hopefully it's now okay. So we are now at week number 12 of the semester. So that means we only have 5 weeks remaining, including this week. So I want you guys to start thinking about your final project, which I think constitutes a huge chunk of your grade. Tama nga ba? It's 20%. So start thinking about it. I'll give you the formal guidelines siguro by Friday, all right, or by tomorrow. And then we'll discuss it a little bit more on Friday, Pero the idea is you can work in groups if you want. You can work solo or by pair, or you can do it in groups of 3 or 4. Pero max na yung 4, ah. Tapos the idea is you will just apply. Inisip ko pa kung ano yung specific conditions for this semester. Pero probably it would be an application of one of the methods we discussed or some other methods na hindi natin na-discuss to real world data. Okay? So pili lang kayo ng isang application, and probably on Friday I can also give you some examples ng mga previous projects so you'll have an idea. The only catch is if you will be working solo or as a part of a pair, you'll just need to submit a written output. Okay, so gagawa lang kayo ng mini research paper with an abstract, introduction, mathematical framework, results and discussion, and then conclusion. And but if you'll be working in groups of 3 or 4, aside from the written output, you'll need to submit a video presentation. All right, presenting essentially what you wrote or what research you did. Okay, so ipapresent nyo lang siya, recorded lang naman, or gusto nyo face to face. I don't know if you guys are still in campus on the probably first week of January. Pero pwede natin pag-usapan. If you want to do it live or you want to do it recorded na lang, that's fine. But the deadline for the project would be on the finals week. All right? Kasi siya yung pampalit natin sa final exam. Instead of, again, testing you in Math 174, I think you are adequately assessed naman, because we do have weekly laboratory classes. We're in week in and week out, you have your exercises. So I don't want to give additional burden to you. I think that's sufficient. So ang pagandaan nyo na lang na medyo mabigat would be the second problem set. So which I'll give probably in 2 or 3 weeks time to give you 1 week to finish. And then, yeah, the final project, which you'll have ample time to do. Siguro I'll also give you a 1 week break. Hopefully, sana matapos natin ng mabilis yung mga natitirang topics para you'll still have 1 week left just to do the problem set and work on the project. But you can continuously work on the project over the Christmas break, though I don't want to ruin your Christmas break. So siguro, yeah, titingnan ko rin yung schedule ng final exam. And I'll try to schedule the deadline for the project as far as possible, para mabigyan kayo ng mas maraming time with your family during the Christmas break. Para first week ng January, pwede nyo siyang gawin. Okay? Pero talk with possible groupmates within the next few days or within the next few weeks para maplano nyo ng maayos. Okay? Kailangan ko lang ng konting panahon para mag-gradean yung final project. Kasi ako rin yung mag-check ng final project. So medyo kailangan kong habulin yung deadline of grades. Yun lang yung magiging constraint natin. Speaking of grading, I think I finished grading all PS 1.1 that is or that are submitted in Canvas. So generally your essays are very good. Ang usual scores is around 9.5 and above. My only comment is yung iba masyadong mahabang sumagot. Ang instruction ay not more than 3 sentences. Yung iba nag 4, 5, yung iba 2 paragraphs yung sagot. So I needed to give some deductions. Yung iba technically ginawa nilang 2 to 3 sentences nga, pero super complex yung kanilang sentences. Ang daming propositions. Hindi lang siya compound eh. Parang ano siya, compound sentences. But I hope you remedy that on the next problem set, ano, kasi medyo mahaba rin. I'm just looking for catchphrases, ano. So hindi ko kailangan yung mahabang sagot. Meron yung iba na 2 sentences lang yung sagot, or 2 sentences yung sagot at nandun na lahat. 2 short sentences, and then they were able to fully express their thoughts. Now, I'm still on problems 1.2. All right. Parang ang natatapos ko pa lang sa problem 1.2 ay hanggang mga letter E yung start ng surname. I'll continue grading, and hopefully within the, anong promise ko sa inyo? I think I promised Friday. So by Friday, I should be able to, or sana, mabalik ko na yung problems. At if not, extension ng weekend, ano. Pero anyway, so that's our housekeeping matters. So now let's oops, hindi ko pala nababago yung yung academic year dito sa title ng modules. But I know you get the idea, and I don't know if you pay attention such attention to these details. But welcome. We are now in module number 8. I think Math 174 has 12 modules or 11 modules, and probably you can skip some of them para mabigyan kayo ng isang libreng week at the end of the semester, just to just for planning the project, and then doing the problem set. So yeah, remind nyo lang ako na nangako ako sa inyo na meron kayong isang free week towards the end, or at least one free week. So, and module number 8 actually starts a brand new chapter. Oy, parang ang saya, no? Ang iksi ng chapter natin on derivatives. Now, what we did is to develop numerical differentiation formulas. Kaya lang ganun kasimple yung derivatives eh. Kahit na yung actual definition ng derivative, right? We define the derivative of a function as the instantaneous rate of change. So basically, it is the limit of f of x plus h minus f of x all over h as h approaches 0, right? That's essentially what the derivative is, right? By definition. Ang ginawa nga natin, isa sa mga low order formulas natin, tinanggal lang natin yung limit. And then we said we choose a step size that is small enough, right? H that is very, very small. Theoretically, this should work, right? So I think this is an order 1 formula, if I'm not mistaken. So we just choose h less than to be much less than 1, then we will get a good approximation, at least on theory. Okay, though we have seen this in I think in LabXor 4.1 na counterintuitive na naman, kasi kahit yung formal definition ng limit once h2 approaches 0, so that's generally our idea, and that is back with an analytic argument by looking at the theoretical error, right? So yung theoretical error na na-derive natin using Taylor's theorem, nag-approach siya ng 0 as h approaches 0, right? And in a much fast way, ano? However, nakita natin na hindi ganun yung laging nangyayari. There's some point that the process will break, essentially when we perform it in a computer, because computers are finite machines. They do truncations. It is prone to cancellation error. And actually, lalo na kapag kayong step size ay mas maliit na dun sa machine epsilon. All right? Actually, hindi nga tayo maabot sa sa malapit sa machine epsilon na 10 to the minus 16. Somewhere around 10 to the minus 15, the process starts to break down, especially for functions that behave in a certain way. Essentially, if f of x plus h is very close to f of x, these two terms in the numerator nearly cancel each other out, or virtually cancels each other out from the point of view of a machine. And I hope you have seen in math or in Amath 152 that that's essentially a phenomenon that we should have expected, because taking the difference of two very small numbers is ill-posed, all right? Or in most instances, taking the difference of two numbers that are very close to each other is ill-posed or is ill-conditioned. So kaya kailangan maging careful tayo whenever subtracting two numbers that are very close to each other. And actually, that will always happen if we are subtracting two numbers that are close to each other and at the same time are very small. Okay, now andito na naman tayo, mga numerical analysts or mga mathematicians, hindi tayo pumapayag na merong unsolved mystery, kumbaga, dun sa ating formulation, ano? So, paisip tayo, kung minsan pala nagbe-break yung ating numerical differentiation formulas, so we cannot theoretically make h very, very small or h approach 0 because machine precision will kick in. What is the optimal h? What is that value of h, or at least the near optimal value of h, that will give us very accurate results without the machine epsilon ruining the process? Yun yung ginawa natin when we look at the optimal step size. Merong isang optimal step size na ibabalance niya yung theoretical error dun sa machine error. When I say machine error, this is the error due to machine truncation, all right? And as you might notice, wala tayong laboratory exercise about the optimal step size, so that should be a clue for you that somewhere in the problem set, in problem 2 or problem 3 of the upcoming problem set, you will work with optimal step size. All right? Hindi ko nakalimutan yung optimal step size. I promise that will appear in the problem set. Okay? Hindi ko na sinama dun sa lab exer kasi masyadong hahaba, ano? Okay. So yun, and then we actually implemented another one, or another improvement for the numerical differentiation formula. So if you want our solution to approach 0 faster, though we cannot select h to be very, very small, so tinignan na lang natin yung mas global na approach, or which is basically we are combining two approximates to get a series or a new sequence of approximates that converge faster, or that converges faster to the actual derivative, and that is via the Richardson extrapolation. So yeah, actually, I have a note that the Richardson extrapolation formula that we discussed in one of our examples is not just applicable to numerical differentiation formulas of order big O of h squared. Mag-apply din yun sa kahit anong formula of order big O of h squared, be it for ODEs, be it for nonlinear equations, all right? But that's for Math 175, ano? So, and then doon na natin isasarado yung libro ng numerical derivatives or numerical differentiation, because there's nothing much to it. And actually, ito yung isa sa mga pinaka iniiwasan. One of the numerical approaches or methods na iniiwasan whenever doing large data computations or large scale computations, lalo na sa applications, kasi napaka-unstable ng numerical differentiation. You see, the contrast between theory and practice. Sa theory, palitin mo dapat si h, dapat gumaganda yung approximation, pero hindi siya laging nangyayari. That makes numerical differentiation to be a very, very sensitive operation. Kaya kung nagre-research na kayo, papansin nyo na bakit kaya gustong iwasan ng advisor ko yung paggamit ng numerical differentiation. Kasi nga, hindi natin matimpla. Kasi somewhere, when we do the computations in our machine, there would be, you will find two very close numbers that you need to subtract from each other when using when using numerical differentiation formulas, and that can cause the whole process to break down. Kaya kung may posibilidad naman na imbes na halimbawa differential equation yung kailangan mong i-solve, right? Kasi pag pag differential equation yung kailangan mong i-solve, malamang mag-difference equation ka, or i-approximate mo yung mga derivatives using the numerical differentiation formulas that we can find from Taylor's theorem, okay? Pero yun nga, unstable yun. So katulad ko, imbes na mag-numerical differentiation kasi ang laki nung data na pinag-workan ko, in-avoid ko talaga na mag-numerical differentiation. I turned the differential equation, actually it's a PDE, tinranslate ko siya sa isang integral equation. Kasi nga yung integral equation, mas stable siya kaysa sa numerical differentiation. And I guess that's a nice segue to the content of module number 8, napahaba yung introduction. Pero module number 8 is about numerical integration, all right? So this would be our topic for the remainder of the semester. Specifically, the basic Newton-Cotes formula would be our our menu for this week. All right, and then you'll have another laboratory exercise on the 28th, right before midnight in deadline. Yeah. And then here are our objectives for the module. Number one, derive basic and composite Newton-Cotes quadrature rules. We'll learn later what quadrature rules are and specifically what are Newton-Cotes quadrature rules. And then, lagi na lang kasama to kasi it's a numerical analysis course. It's not just a numerical methods course. It's not just a programming course. Pero analysis course to. So kailangan nating tingnan ano yung mga error estimates. So ano yung mga upper bound doon sa mga quadrature, sa error, sa mga quadrature rules na to. And then of course, pwede natin itong tingnan sa inyong final project. You will use this quadrature rules to solve scientific problems. Okay? Now, Newton-Cotes quadrature rules. Well, essentially, this is the last chapter. Tapos, ang gusto nating i-address ay paano mag-estimate ng integral ng isang function, ng isang continuous function. Well, there could be several problems na nangyayari kapag involved yung integration, all right? And actually, I think you already know some of them. Can somebody give me, ano yung mga nagiging problema natin sa integration? Sige nga. So what are the problems that you encountered when you are doing integration para ma-justify yung need para sa numerical integration formulas? Kasi baka naman kaya nyo naman palang isolve lahat ng mga integrals, so bakit pa tayo mag-numerical integration? So what do you think are the problems that we encountered when doing numerical integration? Sorry, actual integration. Yes, Giancarlo? Kita ko, tumaas yung kamay mo.
Sir, walang closed form antiderivative.
Okay, perfect. Thank you, Giancarlo. Yun din yung sabi ni Nicolate sa chat. Kasi pag nag-i-integrate ka ng function f of x dx, right? Di ba sabi natin by the fundamental theorem of calculus, this is equal to f definite integral to f of b minus f of a, where the function capital F is the antiderivative of the function little f, right? So, yeah. Ang problema ay paano kapag walang walang closed form yung antiderivative. Ibig sabihin, you cannot find the antiderivative of little f na ma-apply mo yung second fundamental theorem. Some examples ay parang baligtad, no? Parang derivative to ni little f. Ba dapat ito yun. Okay. Yes, capital F prime equals little f. All right. So ano yung mga examples ng mga functions na walang mga closed form antiderivatives like sine of x squared? A very simple function pero kahit anong method of integration, yung gawin mo, wala tayong mahanap na capital F kapag ang little f natin ay si sine x squared, right? So there's no closed form antiderivative for sine x squared. Ano pa? E to the x squared. Wala rin yung closed form. So these are some functions that are very, very simple and yet hindi natin sila kayang i-integrate by hand. Right? So aside from that, may naisip pa ba kayo na problema with antiderivatives? Or integration? Ano pa? Ano pa yung mga na-encounter nyo? Aside from the human factor na nakalimutan yung mag-integrate. Oh, Christian has a very interesting answer, improper integrals. So yes, mahirap mag-integrate ng improper integrals. Actually, hindi siya right away na address in numerical integration formulas. There is a module that I wrote about integration anomalies, and one of them is improper integrals. That's correct. Mahirap mag-evaluate ng improper integrals. But the problem is, when we simply apply our basic quadrature rules or basic numerical integration formulas, may mga problema pa rin tayong may encounter with improper integrals. So we need to tweak the problem a little bit para mag-work yung mga numerical techniques natin for improper integrals. But yeah, that's a nice answer. Improper integrals. What else? Wala na? Wala na kayong maisip na posible maging problema aside from walang closed form? Well, halimbawa merong closed form. So merong closed form antiderivative. So ibig sabihin pwede mo ma-apply itong fundamental theorem. Okay? So ano yung posible maging problema rito? Well, one problem that we can encounter is when capital F is much more complicated than little f, right? And which is usually the case, right? May mga functions na pag in-integrate mo, kinuha mo yung kanilang indefinite integral, mas komplikado yung lumalabas na function, all right? So ibig sabihin si capital F, yung function values niya ay mas mahirap i-compute kaysa sa function values ni little f, all right? So can we take advantage of a knowledge of little f instead of capital F to get an estimate? Because our machines might not be able to optimally compute capital F, right? Wala tayong problema kapag ka si little f ay polynomial kasi ang integral ng polynomial ay polynomials din, and polynomials are perfect match for computers, right? Madaling mag-evaluate ng polynomials. Pero halimbawa, ano bang mahirap na integral? Diba, integral ng ln x. Anong integral ng ln x nga? Tama ba? Ln x minus x. Kalimutan ko. Ay nako, baka example ko to sa 151 mamaya hindi ko siya ma-integrate ng tama. So, but I know for sure the integral of ln x is much more complicated than ln x. So, medyo minsan ganon. Mas mahirap i-evaluate si capital F kaysa kay little f. And you will see later how numerical quadrature formulas shifts the focus to function values rather than the antiderivative. Okay, so yon. That's another possible problem. And sa application naman, ano yung posibleng problem na ma-encounter natin? Bawa, nasa ano na kayo, nagagawa na kayo ng thesis o nagagawa na kayo ng SP. Tapos, kailangan nyo mag-integrate. Pero yung data nyo manggagaling sa totoong buhay or sa measurements, ano yung magiging problema natin if you want to integrate in that situation? Elgin evaluating bounds at infinity. Well, yeah. Pero dun siya papasok, Elgin, sa improper integrals. Kapag ang isa dun sa mga bounds ay infinity. Halimbawa, yung A mo ay negative infinity, yung B mo ay positive infinity. Yes, I guess Ray, Nicolette, and Christian got it. Kapag ka discrete yung data points. Halimbawa, gusto mong kunin yung area ng crater ng Taal volcano. All right? So yun yung pinagawa sa yung SP. Calculate or estimate the area of the crater of di pala Mayon volcano, maliit pala yun. So Taal volcano na lang para mas pronounce yung crater. And actually this is I guess one of the usual projects na ginagawa nila para sa 174, what you'll do is go to Google Maps, tapos kukunin mo yung scale, tapos titingnan mo yung itsura, i-model mo yung shape ng crater ng Taal volcano, all right? Kaya lang, pipili ka ng discrete set of points. Yun yung magiging measurements mo. And then, instead of integrating a function, you are supposed to integrate over that discrete set of points. Pero paano tayo mag-i-integrate kapag discrete lamang yung set of points natin? All right? And then I remember another project that I did actually with an undergraduate then. Minodel namin yung butterfly effects sa traffic. All right? Kasi nga yung traffic ay pwede mong kasi yung velocity ay integral lamang ng displacement, And then the acceleration and velocity is the integral, baliktad pala. Ang integral ng acceleration ay velocity. Ang integral ng velocity ay displacement. Ano? So, tiningnan namin yon, minodel namin yung movement ng traffic. Ano yung mangyayari kapag yung nasa unahan ng traffic ay or isang car sa medyo unahan nung road ay nag-slow down by a little. Ano? Malimbawa, nagbawas lang siya ng 5 miles per hour. So magbabawas siya ng 5 miles per hour. Ano yung magiging epekto nun dun sa traffic behind him? Napakita namin na kahit walang aksidente, walang intersection and so on, kapag ka nag-slow down yung unang vehicle, ano, tapos marami ng vehicle dun sa traffic, kahit magkakalayo pa sila, there is a point that those in the back of the road will be at a standstill kahit nagbawas lang ng 5 mph yung nasa unahan. And ginamit namin ay numerical data. We have data of average speeds, displacement, acceleration, and then kinailangan namin mag-integrate. Halimbawa, ang given na data ay acceleration, right? Or nagbawas ng acceleration, depende dun sa type ng vehicle, paano siya nag-accelerate. So kailangan namin integrate to get the speed, tapos to get the displacement, we need to integrate again. But our problem was, paano ko to gagawin? Wala namang function na binigay. Pag nagda-drive ka ng car, wala kang function na magmo-model dun sa iyong speed. Okay? Meron ka lang ay discrete measurements, snapshots in time. About time t equals 1, ito yung speed mo. After 1 minute, ito na yung speed mo and so on. And then you can compute your average speed. So ganon. Usually sa totoong buhay, wala talagang function. And ito yung sabi nga nung marami sa inyo, yun yung isa sa mga realization nyo na hindi natin lagi nagagamit yung calculus techniques kasi nga sa totoong buhay hindi naman ganun ka-perfect yung data. Usually ang nakukuha natin na data ay snapshot lamang ng buong pangyayari. Alright? Kasi wala tayong measurement for all time values. Alright? So I think those are the three major problems or concerns na na-encounter natin sa numerical na-encounter natin when it comes to integration. And these are some of the things that we want to address using numerical integration formulas. So there are basically two types of two types of integration formulas that at least we'll be talking about in this course. Yung una ay quadrature rules. And I think the first two modules will work on these. So quadrature rules. So ito yung medyo mga deterministic na methods. And the idea here is actually may dalawa pa tong sub-classifications, but I'll talk about that later. Pero in general, quadrature rules look like this. Ang integral from a to b ni f of x dx, the only requirement is that f is continuous or is a piecewise continuous function. All right. Laging mag-exist yung definite integral. And we will approximate this with summation of some constants. Tawagin natin w sub I times f of x sub I going from 0 to say capital N. Medyo nag-shift ako dito ng indexing dun sa module. I don't remember why. Bakit kay 0 ako nag-start ng indexing dito? So kailangan nyo siyang i-adjust when you will write a program in MATLAB, right? Pero yung idea lang dito ay, yung integral, papalitan ko lang siya ng constant times function values. Summation ng mga constants times function values. And you will see here that we are directly addressing the concern of the antiderivative being non-existent or the antiderivative being more complicated than the function f itself because wala tayong antiderivative na ginagamit sa mga quadrature rules. You will see that what we are doing is taking a bunch of function values. So we are choosing n plus 1 points, kukunin ko yung function values, little f at those n plus 1 function values. I multiply them by some weights, and then I'll add them up. And that summation will be my approximate for the integral. Right? So ito yung mga quadrature rules. Kukunin mo lang yung linear combination ng mga function values. Right? The thing is, how do we solve for w sub I? Kasi usually yung f of x sub I ay kaya mo yung computin. because given yung function f. So it's easy to compute function values, and then we can usually choose what are the exabytes that we will be using. Ang problema ay paano natin PPDN yung mga weights. And that's where the different types of quadrature rules diverge. So meron tayong Newton-Cotes formula, tapos meron tayong mga Gauss-Legendre formula. Parang naputol ako doon, pero I hope I'm back. In-address din niya yung problema na discrete lamang yung data na meron ka. Because you see here, it's just function values times some constant. Kukunin mo yung summation, so you don't really need how f really looks like over the entire closed interval AB. Kailangan mo lang ay mga function values ni little f at some points exaby within the integration interval a comma b. So it would be perfect for real-world data. Okay? So paano mo nga lang pipiliin yung weights? Then yun yung pag-aaralan natin later. Okay? Tapos meron pang isa, which I hope to discuss, yung Monte Carlo simulations. I think some of you might have heard of it, simulations, which is sort of a non-deterministic. So meaning ito ay isang probabilistic method wherein you simulate thousands or hundreds of time. Kukunin mo lang yung mga random summation ng mga function values. Ano? So parang ano lang siya, randomization ng summation ng function values times probably some weight here in the beginning. Tapos ang pagpili mo ng exabytes ay random. Alright? Pipili ka halimbawa 1 million points. So I from 1 to 1 million. Tapos pipili ka lang randomly ng mga exabytes. Kukunin mo yung function value ng mga random exabytes na yon, function values nila. Kunin mo yung sum, multiply the sum by some weights, and then you'll get an estimate for the integral. But since there is no science to the choice of the exabytes or the weight, usually ang weight lamang ay length of the interval, ano? Or scaled by the number of points used. Pero ang idea ay gagawin natin ito ng paulit-ulit. Kasi by the law of large numbers, if you do an experiment, a random experiment, sufficiently large number of times, all right? Paulit-ulitin mo ang isang random experiment, it will stabilize around an expected value. So yung mga nagawa 8-1 dyan, you have heard of the expected value. Kaya expected value yung tawag sa kanya. Kasi in the long run, ganun yung magiging value niya. And then when you perform this experiment, the expected value actually is the integral of f of x from a to b. Because I hope these two summations remind you of something. May naalala ba kayo dyan sa dalawang summations na yan? With regards to integration, I hope you have seen this. Siguro sa Math 30, kailan kayo nag-aral ng integrals? Math 37 na nga ba? Never pa ako uli nakapagturo ng 36 and 37 since binago siya noong 2018. So, hindi ko na alam. I think Math 37 nga ba? So, do these two integrals remind you of something? Oh yes, very good, Nicolette. So this is basically the Riemann sum. Yung remember, laging sa introduction ng integral, may curve, tapos magdodrawing ng mga rectangles, ano? Tapos yung rectangles na yan, kukunin mo yung area, length times width, pero yung length niya ay magiging function value, tapos yung width ay yung delta x. So basically, ganito yung nagiging itsura nila. It's why it is justified that when you take the limit as n approaches infinity, this will be the Riemann sum, all right, or the Riemann integral, and that is definitely equal to the integral. So ganun lang, imbes na infinite yung proseso, all right, ginagawa natin siyang discrete, ginagawa nating finite yung process. Instead of taking the limit as n increases without bounds para makuha yung Riemann integral, pinuputol natin yung summation not to go to infinity, but just to go to a sufficiently large number. All right? Or pwede tayo mag-compensate. If we cannot make n very, very large, siguro galingan natin yung pagpili ng weight. Para doon yung weights eh. Pero sa Monte Carlo, I think this is much more pronounced that kailangan mo lang napakaraming points para makuha yung magandang approximation dun sa function value. But let's focus more on quadrature rules for now and leave Monte Carlo simulations for a later module. Specifically in this module, we'll talk about the Newton-Cotes quadrature. May dalawang klase ng quadratures. Newton-Cotes tayo ngayon, and then probably next week we'll do the Gauss-Legendre quadrature rules. Right? Pero again, the general form for quadrature rules, kailangan nating makahanap ng formula ng itsura ay weight times function values. And then we're taking the summation. Now, the idea behind Newton-Cotes ay isang usual idea for you, right? And this is perfect whenever you have discrete data points. Gagawin mo lang kapag given sa yung f of x sabay, right? Ang kailangan mo lang gawin ay kunin yung kunin yung interpolating polynomial na daraan doon sa mga points na yon. Right? So kung given ka ng 10x, f of x, kunin mo lang yung interpolating polynomial na daraan dun sa mga x's na yon, tapos i-integrate mo yung interpolating polynomial. Because we won't have any problem about integrating polynomials, because integrals of polynomials are still polynomials and they can easily be done in computers. So kaya napakahalaga nung unang half nung ating ano sinasabi ko, sorry, na-distract ako, may nag-chat kasi. So, importante yung unang half ng ating course because basically, yun yung pwede nating gawing nating fail-safe method. Whenever we have a discrete set of data and we want to do calculus tricks on it, either integration or differentiation, what we can do is to take the interpolating polynomial for that discrete set of data and perform the differentiation and integration on that interpolating polynomial, and we will get an estimate for the actual derivative or the actual integral. And that's what Newton-Cotes quadratures do. Kasi gagawin ito kapag given ka ng halimbawa distinct function values or a set of function values, kunin mo lang yung interpolating polynomial and you integrate the interpolating polynomial. And basically, there you have it. Yun na yung Newton-Cotes quadrature, end of module. Kasi ganun lang talaga siya kasimple. Or kahit na halimbawa, given si little f, nagpapa-integrate ng e to the x squared all over some interval. And then we know that it doesn't have a closed form antiderivative. Then pwede mong isipin ilang points yung gusto mong gamitin. Halimbawa, gusto mong gumamit ng 100 points. E di kunin mo yung degree 99 interpolating polynomial para kay e to the x squared, and you integrate that degree 99 polynomial. And that's no biggie, kasi kahit degree 99 yan, polynomial siya, ang dali niyang kunan ng integral. Okay? So now, let's look at specific Newton-Cotes quadrature formulas, but essentially that's the idea. All right. So I think here our notation, if I want to integrate f of x from a to b, I will approximate it by quadrature rule. So si Isaben, ito yung quadrature rule that uses endpoints. Okay. So which we will define to be the integral of the degree n interpolating polynomial. So pinalitan ko lang talaga si little f by the interpolating polynomial, right? So yung interpolating polynomial, either by necessity, ang pagkaka-define mo sa kanya, meaning kasi yun lang yung data na binigay sa'yo. Halimbawa, you are integrating a price function, meron ka lang data when x is 0, 10, 20, 30, 50, 60, 70, 80. So wala kang choice, yun lang yung data points na gagamitin mo. Pero it could be your choice kapag given sa'yo actually yung function little f, ikaw yung pipili kung ano yung mga x's na pwede mong gamitin. Alright? But essentially, in either case, you're gonna get an interpolating polynomial. Tapos natutunan natin sa chapter 1, yung P-sub-n, meron siyang Lagrange form. Ano yung Lagrange form nun? It is just the summation of the given function values or the chosen function values times little L sub I, where little L sub I are our Lagrange basis polynomial, if you still remember it from chapter 1. Ito yung itsura ng Lagrange basis polynomial, yung multiplier dito sa summation na to. Okay? And then I'll just interchange the integral and the summation because we know that integrals are or integration is a linear operator. So ibig sabihin, pwede natin pagpalitin yung order ng integration at saka summation. So pagbaligtarin natin yan. So ito ay magiging integral, tapos ito ay magiging summation. Pero itong f of x ay constant yan with respect to x kasi mga function values yan. So pwede siyang lumabas ng integral. That's why itong f of x sabay nakalabas ng ating integral. Tapos, ang matitira na lang sa loob ng integral ay yung integral ng Lagrange basis polynomial. And then you compare it to the general form of a quadrature rule. So what can you say about this quadrature rule? Or is it really a quadrature rule? Yes, it is really a quadrature rule because it is a linear combination of the function values, right? But what are the weights associated to each function value? Sige nga. Kasi 'di ba yung Lagrange ay yung ating quadrature rule, sabi ko ganito dapat yung itsura niya. So where the W sabays are the weights. Now, if you're using Newton-Cotes quadrature, which is basically the integration of an interpolating polynomial, what are the weights in this quadrature rule? Habang sasagot ako ng chat, ano? Yes, Ray and Mitzi are I know what you're talking about, pero yeah, kasi chat, no? So hindi nyo ma-explain ng mahaba. Nag-explain pa si Mitzi. Yes, the weights are actually the integral of the Lagrange basis polynomial. Ito yung weights. Ito yung W sabay sa Newton-Cotes formulas. So humabol si Dino. I don't know, Victor, what you meant by fx. Is that f of x? But remember, ito yung f of x ko, function values, nandun na talaga siya sa quadrature rule. Yung pang-weight dun sa mga function values ay yung W sabay, siya yung integral ng Lagrange basis polynomial. And yeah, and that's easy to compute, right? Because yung Lagrange basis polynomial, product lamang siya ng x minus x sub j over x sub I minus x sub j. All right? So if it's too technical, that's fine. Pero isipin nyo lang, Newton-Cotes, pwede kong gawin. Bumalik kayo dun sa program. Bumalik kayo dun sa program na sinulat nyo way back in, kailan ba yun? Sa Exer 1 yata, nag-Lagrange interpolating polynomial na tayo doon, no? Sa lab Exer 1 pa lang. So kung meron akong ipapa-numerically integrate sa inyo using Newton-Cotes formula, bumalik lang kayo dun sa program nyo yung chapter 1. Program sa chapter 1, ibibigay niya sa inyo yung AIP. Alright? So pag nakuha mo na yung AIP, i-integrate mo lang yung AIP. Pwede mo nga ipa-integrate kay MATLAB yung AIP and there would be no long computations for that kasi madali lang talaga mag-compute ng integral ng polynomial, and then that's your Newton-Cotes quadrature estimate for the integral. All right? So actually, pwede ko na nga tapusin dito yung lecture eh. Kasi yun lang talaga yon. Ang weights nito ay yung integral ng Lagrange basis polynomial. At kung hindi ko naman ipapakompute yung weights, diretso ka na eh. Kunin mo lang yung interpolating polynomial mula sa chapter 1 program natin, i-integrate mo lang siya, and there we go. That's your Newton-Cotes quadrature estimate. Okay? But of course, let's look at some specific cases. Actually, meron ako dito diniscuss na dalawang klase ng Newton-Cotes formula. Meron akong tinatawag na closed formulas at saka open formulas. Well, usually these are for equally spaced abscissas. Kapag ka equally spaced yung mga x's na ginamit mo dun sa pagperform ng interpolating polynomial, then you can have closed or open formulas. Closed formula siya kapag kasali yung endpoints doon sa abscissas. So kung kasali si AB dun sa mga data points na ginamit mo para makuha yung interpolating polynomial. Now, you will have an open formula if hindi kasali si A at saka si B doon sa yung pag-i-interpolate. Kailan useful na hindi kasali si A at saka si B doon sa endpoints? Well, actually, ano siya? Kapag ka improper integrals. Kasi di ba, or certain types of improper integrals. Kasi alam natin, kapag ka improper integrals, posible na discontinuous yung ating integrand at one of the endpoints. If that will happen, then we can simply forget about the endpoints, right? We get sufficiently number of data points within the open interval. Kaya open formula yung tawag sa kanya. Kasi pumipili tayo ng mga x's dun sa open interval of integration. Hindi natin sinasali yung endpoints. Because there could be some problems with the endpoints like the discontinuity of your function little f or si little f ay hindi defined dun sa isa sa mga boundaries. So there's no point in using the bounds of the integration interval. All right? Pero kung wala namang problema, edi gamitin mo na yung closed formulas. Kasali si A at saka si B doon sa endpoints, doon sa interpolation process. Now, if we will be using n plus 1 points, and then we want to use equally spaced points, then ang ating step size for the closed formulas ay b minus a over n. Of course, there are no requirements as to the increment. Hindi kailangan ay equally spaced yung mga abscissas na gagamitin nyo kasi nga sa interpolation, wala tayong problema kahit gaano magkakalayo yung mga exabytes kahit hindi uniformly spaced. Yung mga exabytes, kaya natin siyang kunan ng interpolating polynomial. Ganon din dito, no? Pero for simplicity, ang dinerive ko lang dito ay yung mga closed formulas and open formulas na equally spaced, yung mga abscissas na ginamit. But of course, if you don't have control over the data, halimbawa, given lang talaga sa'yo ay certain f of exabytes, so posible na hindi equally spaced yung magagamit mo. Hindi mo magagamit itong mga formula na to. Kasi itong mga formula na dinerive ko, ang assumption ko ay equally spaced sila. Okay? Now again, if you will be using closed formulas, ito yung step size na gagamitin mo that will give you n plus 1 data points starting from A and ending with B. Alright? Ang formula ng mga exabytes ay A plus I delta X. I going from 0 to little n. Pero kapag ka open formulas, kailangan mo pa rin ng n plus 1 points, pero hindi kasali yung dalawang n points. So, hindi kasali si A at saka hindi rin kasali si B. So to complete the set of n plus 1 data points, you need a smaller step size. So yung step size na gagamitin mo ay B minus A all over n plus 2 kasi nga hindi kasali yung dalawang n points. So kailangan merong madagdag na dalawang points doon sa open interval. Kaya mas maliit by 2 yung mas malaki by 2 yung denominator ng step size para sa open formulas. And then still, and now the formula for exabytes, A plus I plus 1 delta X. Kasi si I plus 1, hindi yan pwedeng mag-0 kasi dapat mag-start tayo sa A plus delta X. Kasi nga hindi dapat kasali si A dun sa ating endpoints. Okay? So this will give you a set of data points from A plus delta X until B minus delta X. Kasi bawal sa open kasama yung boundaries ng integration interval. Okay? Now, dahil 1 minute na lang, matatapos na yung klase. Daldal ko kasi. Pero medyo, sige, mamaya na lang para masaya yung ending ng klase. Alright, quickly, give me 2 minutes. Papakita ko yung pinakamaiksi na closed formula. So yung pinakamaiksing closed formula ay, what do you think? Dalawang data points yung gagamitin. Spoiler kasi na-flash ko na siya sa screen. Kasi di ba sa closed formulas required, na gagamitin mo yung left at saka right endpoint. So the minimum closed formula should involve 2 data points. Yung A, F of A at saka yung B, F of B. Alright? Now, if we have that, then we'll be using I sub 1. Kasi nga si I sub 1, ito yung may dalawang data points. Remember, meron tayong n plus 1 is equal to 2. This is the number of points in the interpolation. So kapag ka meron tayong n plus 1 equals 2 na data points, so ibig sabihin makakakuha tayo ng linear interpolating polynomial. Kaya naman ito yung I sub 1 na quadrature rule. Right? Tapos kung matatandaan nyo, kapag meron akong dalawang data points, a, f of a, tapos b, f of b, you'll get the interpolating polynomial, p sub 1 of x, which is basically f of a times x minus b over a minus b, plus f of b times x minus a over b minus a. Ito yung Lagrange form ng interpolating polynomial. So here are your function values at saka linear lamang yung mga Lagrange basis polynomial kasi degree 1 lang dapat si p sub 1. Okay? Tapos ang pangako ng Newton-Cotes quadrature, i-integrate mo lamang yung interpolating polynomial. Tapos yun na yung estimate natin para sa integral. So integrate ko yan, dx, integrate ko to, dx, say interval a to b, interval a to b, alright? Tapos pwede ko yung i-simplify. Si f of a, constant naman yan with respect to x, so pwede siyang lumabas. So f of a, integral na lamang nung Lagrange basis polynomial as promised, right? Then this is f of b times integral ng Lagrange basis polynomial associated to the second point. Tapos ito, linear lang to, ang daling i-integrate, okay? So integrate mo to, you'll get this guy. Integrate mo to, you'll get this guy, all right? Remember, a and b are just constants, so you can easily integrate this. Kasi for instance, a minus b will come out. So kaya meron ka dun sa denominator. So integral lang ng x minus b with respect to x. You're gonna get x squared minus bx. But you'll appeal to the fundamental theorem of calculus. Ipa-plug in mo si a at saka si b. Ganun din dito sa kaliwa. Tapos you simplify it, and then there you go. This is our Newton-Cotes. This is the 2-point open Newton-Cotes quadrature rule, NCQR. All right. So it's a 2-point, not open, closed. It is a 2-point closed Newton-Cotes quadrature rule. Kasi nga, ito yung function values, tapos ito yung kanilang weights. Ang weight para kay f of a ay b minus a over 2, which is actually what? That's the midpoint of your interval, all right? And then the weight for f of b is the same thing, b minus a all over 2. Okay. And then you can factor out b minus a over 2. You're going to get this, but that is precisely the trapezoidal rule. All right? So yung natutunan nyo saan nyo ba ito natutunan trapezoidal rule? Sa Math 37 din ba? O sa high school pa lang nag-trapezoidal rule na kayo? So ito, dito na-derive yung trapezoidal rule. Yung trapezoidal rule na natutunan nyo before, ano pala siya? Na-derive siya by integrating the interpolating polynomial of degree 1 using the endpoints of my interval, which makes sense because if you have a function, this is a, this is b, you get f of a there, you have f of b here. Yung interpolating polynomial lang naman ay passing through 2 points is basically a straight line, right? So straight line lang yung interpolating polynomial. So instead of the fancy Lagrange interpolating form, pwede mo siyang tingnan what's the line passing through the 2 endpoints. Tapos kukunin natin yung area nito as our substitute for the actual definite integral. But what do we have here? We have a trapezoid. And the formula for the integral of the trapezoid is this guy, which turns out to be also what we'll get if we integrated the degree 1 interpolating polynomial, but that should have been expected, right? Kasi nga function values yung gagamitin natin. Kailangan gamitin yung dalawang endpoints, then that's it. Okay? Now, I will start the lecture on Friday by flashing the trapezoid, the other familiar Newton-Cotes. Actually, pina-flash ko na nga siya ngayon. Yung Simpson's 3/8 saka Boole's rule. Hindi ko pa rin na-edit. Boole's rule lang yan, hindi Boole's rule. All right. So titingnan natin yan next time. And then we'll also look at some open formulas. And then sa lab sa Monday, pagpapahingayin ko kayo sa Monday, papadiscuss ko sa lab instructors nyo yung second half netong handout, yung deriving the composite rules. Ano? So make sure to attend your laboratory classes on Monday kasi didiscuss nga nila yung composite trapezoidal rule at saka yung composite Simpson's rule, I think. All right. So para makapahinga naman kayo, wala tayong laboratory exercise on Monday. But my only request is that you attend your lab classes on Monday. Right? Tapos mafe-feel nyo na ngayon na medyo nagmamadali na ako kasi babawasan ko yung pagpapalab exer. Gagamitin natin yung lab para naman makapag-discuss kayo. Training din to para din sa mga lab instructors nyo kasi yung karamihan sa kanila mga bago sa 174S. So I want them to experience how to deliver a lecture para naman may pasa ko na sa kanila yung 174 in the next years. And then, yeah. Nagmamadali na kasi gusto nating matapos yung course, matapos yung modules, pero I don't want to sacrifice yung details nung discussion kasi ang daming insights na ang gandang i-discuss. Aside from the methods itself, I could have just flashed or given you the numerical integration formulas, pero magandang maintindihan ano yung intuition behind these formulas na sasauluhin nyo yung pwede nyo sauluhin yung Simpson's rule, yung 3/8 rule, trapezoidal rule, saka Boole's rule. Pero pwede nyo rin siyang tingnan in another fashion. You can think of, sa Simpson's rule, kukunin ko lang yung quadratic interpolating polynomial using f of a, f of b, and then the midpoint, f of a plus b over 2, and then get the interpolating polynomial, integrate it, you'll get the Simpson's rule. 3/8 rule, kailangan mo lang ng 4 na equally spaced data points from A to B. Tapos, i-integrate mo lang yon, you're gonna get the 3/8 rule. And so on. So, magandang tingnan yung isang bagay through different perspectives. All right? And yeah, I think that's it. Let's stop here. Any questions, burning questions? Okay. So if there are none, thank you guys for waking up early. I know some of you are also having troubles waking up early for the 8:30 class. Me too. Yun yung magiging problema ko pagbalik natin sa face-to-face next semester. Kasi kailangan 2 hours before class, gising na ako para makakain, makapag-prepare. Biyahe pa kasi ako pa LB. Pero yon, mamimiss ko to. Itong pwedeng 5 minutes before class ako bumangon, kukuha ng kape, bukas ng Teams, and so on. Pwede na magklase. But anyway, so thank you guys for coming. Enjoy the weekend. Attend the lab on Monday. Wala tayong lab extra for the week, for you to relax a little bit at para mabigyan ako ng time na mag-check at saka yung mga lab instructors to catch up. They'll discuss the composite rules, but until then, keep safe guys. See you on Wednesday. Bye-bye. Ay sorry, hindi pa pala weekend Magmi-meet pa pala tayo ng Friday. Sorry, may klase tayo sa Friday yeah, bakit gusto ko na mag-weekend? Sorry. Pahiya ako doon. Bakit have a good weekend? Wednesday pa lang. Nahalata tuloy. But anyway, thank you guys. Bye-bye. May classes sa Friday Kala ko Friday na.